All right, so here we go. It's going to be a fun one. We're given the graph of f prime. So here we have the graph of f prime, and it's the derivative of f. All right, so no surprises there. We know f prime is the derivative of f. But what we're going to do is we're going to use this graph of f prime to sort of uncover, well, what is the original function doing? All right, so let's start with the first question here. What is the slope of the graph of our function f when x is equal to 1? And so we know the slope of our graph, slope of f at x equals 1, well, that's what the derivative is measuring. F prime of 1 really tells us what the slope of the original function is at x equals 1. So we just need to evaluate what's f prime of 1. Well, we go to the graph of f prime. We find the corresponding point on our graph. This has coordinates 1, 2. And so the value of our derivative, if we're looking at the graph of our derivative, which we are, the value is the y value there. So this is just 2. So the slope is 2. So if we know the graph of f prime, we essentially know what the slope is for the original function f at any of these different x values. Okay. Another question. What value of x does the graph of f have a horizontal tangent line? Well, horizontal tangent line means slope is 0. So that's one thing we should kind of get in the habit. It should be almost reflexive now. Horizontal tangent line means f prime is equal to 0. So we're given the graph of f prime, and we want to locate, well, where is the derivative? Where is it equal to 0? And these are the x-intercepts, where it crosses the x-axis. So that's what we're looking for. To figure out where our original function has a horizontal tangent line, we want to figure out, well, where is f prime equal to 0? And since we're given the graph of f prime, that's where it crosses the x-axis, where it touches the x-axis. And we see that right here at x equals 3. This is an x-intercept. And we're talking about the function the graph of f prime here. So this is an x-intercept of f prime. And so what's happening here is this, we have a horizontal tangent line at x equals 3. Because that's where the graph of f prime looks like it crosses the x-axis, where the derivative is equal to 0. Okay. Maybe there's other points somewhere else, but based on the information we have, this looks to be the only place where it crosses the x-axis. All right, part 3. Find the intervals where f prime is positive and the intervals where it's negative. All right, so positive means we're given the graph of f prime, so that means above the horizontal axis. So it looks to be right over in here. So f prime is positive on the interval from, when it trails off like this, we just kind of assume that it keeps going in that direction. Same thing over here. So we're just assuming that because f prime looks like it's above the horizontal axis over here, it's going to be positive from minus infinity to 3. And then from 3 onward, once we hit this point at x equals 3, from 3 onward, the graph is below the horizontal axis, so that means f prime is negative. So from 3 onward, f prime is negative. And that's again because we are looking at the graph of f prime. This is not the graph of f. Important to note that here. So we're not given the graph of f, we're actually given the graph of f prime. So to find the intervals where f prime is positive, we're just looking to see, well, where is the graph of f prime above the horizontal axis? And to find where it's negative, we're looking for the intervals where it's below the horizontal axis. All right, so if we know f prime is positive on this interval, well then, to answer the next question, find the intervals where f is increasing. Well, if f prime is positive on this interval, that means our original function, which graphically we do not know what f looks like. This is the graph of f prime, but based on this information, we know f prime is positive, so f must be increasing on that interval from -infinity to 3. Okay. Well, we also know f prime is negative on this interval from 3 to infinity. So we have no idea what the graph of f looks like. We're not given the graph of f, but we can say f must be decreasing on that interval. So if f prime is negative on that interval from 3 to infinity, well then the original function, f, which we do not have a picture of, we know it must be decreasing on that interval. All right. And then we want to explain why f has a relative max at x equals 3. All right, what's happening at x equals 3? Well, if we notice, that's where the derivative is 0, and our graph switches from increasing to decreasing. So function f switches from increasing to decreasing at x equals 3. And so if we're looking at f prime here, the graph of f prime definitely doesn't have a local max at x equals 3. You know, this is definitely not a local max. But we're not actually talking about f prime here. We're talking about the original function f, which is not pictured. But based on this information that we're kind of digging through about f prime, we're actually able to determine that f has a relative max at x equals 3. And the reason is because the graph switches. It goes from increasing on the left side to decreasing. So if we were to kind of start sketching what f, or thinking about what f might look like, it would go from increasing on one side. So the graph of f would go from increasing on one side to decreasing on the other side, and it kind of has a smooth or rounded transition because we know we have a horizontal tangent line at x equals 3. So it goes from increasing and then it kind of rounds off, and we have a local max at x equals 3. So if we were just to kind of start sketching what f would look like, based on what we have so far, this is what it might look like. It goes from increasing, flattens out, then starts decreasing, and we have a local max at x equals 3. All right. Let's keep digging. So there's a lot more information we can get out of f prime here, and it's going to tell us information about f. All right, so let's find the intervals where f prime is increasing and the intervals where f prime is decreasing. So now we're talking about where f prime is increasing, decreasing. So now we're actually looking at the graph of f prime. So where is this graph increasing? Well, if we read left to right, it doesn't look like this thing's increasing at all. So f prime increasing, I would say none. Doesn't look like there's an interval where this thing's moving up. It's, as we read left to right, the graph of f prime here is just falling. So it's decreasing. So I would say f prime looks to be decreasing on the interval from -infinity to infinity. Okay. So notice, again, we're asking for the intervals where f prime is increasing, decreasing. We already know the intervals where f is increasing, decreasing. That involve knowing where f prime was positive or negative. Now we're looking at, well, where is this graph increasing, decreasing? All right. So if f prime is increasing, that means f double prime is positive. And if f prime is decreasing, that means f double prime is negative. So to answer this seventh part, find the intervals where f double prime is positive or negative. Well, if f prime is increasing, if that doesn't happen, then that means f double prime being positive is not going to happen. So none. And if f prime is decreasing on this interval from minus infinity to infinity, well then same thing is going to happen for where f double prime is negative on that same interval. So kind of like what we did, going from where f prime was positive, negative, going to where f was increasing, decreasing, we're kind of going in the opposite way with f prime and f double prime. So we know where f prime is increasing, decreasing, and we're using that to get information about f double prime. Well, now that we know what's happening with f double prime, we can figure out what's happening about the concavity, the shape of our graph. So if f double prime is positive, that means f is concave up. And if f double prime is negative, that means the graph is concave down. So to find the intervals where f is concave up versus concave down, well, we look where f double prime is positive, no intervals, so there's not going to be intervals of concave up. Intervals for concave down, well, we figured out this was the interval for where f double prime is negative, so that's going to be the same interval for concave down for our original function f. So these are kind of fun to do. And really just to emphasize what's happening here is if f was increasing, that means f prime is positive. Or if f prime is positive, that means f is increasing. And if we apply the derivative, that means f prime is increasing and f double prime is positive. So that same relationship still works even if we apply the derivative. So if f is increasing, f prime is positive. If f prime is increasing, then f double prime is positive. And that's what we used here. So there's a lot of information that we can uncover about our original function by just looking at the graph of f prime. So we were able to figure out where f is concave up, concave down, just by looking at the graph of f prime. We were able to figure out the intervals where f is increasing, decreasing, just by looking at the graph of f prime. We were also able to determine that our graph of f has a local max at x equals 3. Again, just by looking at the graph of f prime. So there was quite a bit of information that we were able to extract here. And we were actually able to kind of get a preliminary sketch of what function f might look like. And notice that this sketch even agrees with what we found for the shape. We figured out that the shape of our graph must always be concave down. And when we started sketching this, that's what it was going to look like, concave down. All right, so this one's a good practice, and we're going to be talking about these ideas over the next bunch of lessons. So we're gonna keep practicing with these ideas and these definitions. So we'll see you then. Bye-bye.